Okay, so for the last section that I'm going to do by video, conservation of momentum, probably one of the most important laws in all of physics, is the idea that momentum is conserved. Now, the term conservation in this sense does not mean we're trying to save it for future use. What it means is that momentum can neither be created nor destroyed. Okay, and before we get into the mathematics of this, I want you to think about a question. Say you have a rubber ball, a ball that bounces, and a sticky clay ball, each with the same mass, and you're trying to knock over a wood block. This is similar to the carnival festival game where you're given let's say 2 balls, you're trying to knock over the milk bottles, milk jugs. If you were given a choice of a rubber ball or a sticky ball, which one would you choose in order to knock over the wood block? So normally I'm going to show this in class when we get back together, but for now I want you to think about this, and by the end of this lecture, by the end of this chapter, you should have a good idea of which would be the better choice. Okay, so conservation of momentum tells us that if we define a system in which there are no external forces acting, so here's our system, 2 objects, 1 and 2. They each have some velocity beforehand, therefore they have a total momentum, a total initial momentum. If we ignore any, or if we're able to ignore any external forces, so the only forces acting on these balls are ones due to each other because they are part of the same system, then after the fact, after the collision, the final total momentum of both particles will equal the initial total momentum. So the total initial momentum equals the total final momentum. The important thing when we do this is to define our system in a clever way such that all forces are all internal forces, internal to the system. We're going to ignore any interaction with the environment. Okay? Ignore the environment. So the law of conservation of momentum states that the total momentum of an isolated system is constant. The key here is isolated. No external forces. No external forces. Interactions within the system, so these Newton's third law pair forces, do not change the system's total momentum. So this is what we would write mathematically. Let's see what this looks like with a couple of examples. First of all, we have a curling stone. If you don't know what curling is, here's an example of, I think, the Swedish Olympic team. Has a mass of about 20 kilograms sliding across the ice at 1.5 meters per second. It collides head-on with a stationary hockey puck of 0.16 kilograms. After the collision, the puck's speed is 2.5 meters per second. What is the stone's final velocity? Okay, so for this problem, as always, we want to start with a picture. So initially, we have a curling stone. I'm going to call it mass of the stone, with some initial velocity. So this is the velocity of the stone initial. And it's going to hit a hockey puck, I'm going to call it M sub P for puck, that has 0 initial velocity. So here's my before picture. Before. Then there's a collision between the two, and the curling stone, I'm going to assume it slows down a little bit. So here's the velocity of the stone final, and the puck, here's the puck, mass of the puck, is going to have some final velocity, V puck final. Okay, so here's after the collision, before and after the collision. So the initial momentum, we know, is equal to the final momentum. Now all of these velocities are to the right, so they're all positive. So I can get rid of my vector symbol. And I know initially the only momentum I have is the mass of the stone times the velocity of the stone initially. And that's equal to the total final momentum, which is the mass of the stone times the velocity of the stone final plus the mass of the puck times the velocity of the puck final. Now I should also have my table of knowns, so let's do that on the side here. So I was given the stone's mass of 1.5 kilograms. Oh, no, sorry, 20 kilograms. The mass of the puck was 0.16 kilograms. The initial velocity of the stone was 1.5 meters per second. Decimal there. And I was given the velocity of the puck after the collision. So V puck final is equal to 2.5 meters per second. Okay, so I'm asked to find the final velocity of the stone. So I'm going to solve for that here. And solve for that there. So the mass of the stone times the velocity of the stone final is equal to this term, mass of the stone times the velocity of the stone initial, minus this term, mass of the puck, velocity of the puck final, divide by the mass of the stone. So the velocity of the stone final is equal to mass of the stone, velocity of the stone initial, minus mass of the puck, velocity of the puck final, all divided by the mass of the stone. Now if you plug in numbers here, you should get 1.48. And the units, well, I have mass on top and mass on bottom, so the kilograms will cancel, and I'm left with meters per second. So 1.48, that's slightly less than my initial velocity. Does it make sense that it's changed by such a small amount? Well, sure. Since the mass of the stone is so large compared to the mass of the puck, we would expect a small change in velocity of the stone to correspond to a large change in velocity for the puck, which went from 0 meters per second to 2.5 meters per second. So this seems reasonable to us. If we are working in multiple dimensions, we can still apply the law of conservation of momentum. We just have to break it down into x and y components as we normally would. So we can write the total final momentum in the x direction is equal to the total initial momentum of all of the particles in the x direction. Likewise, the total momentum in the y direction is equal to the final is equal to the total initial momentum in the y direction. So you basically have to break up initial is equal to final, and then have one equation in the x direction, another equation in the y direction, and if I were feeling particularly sneaky, I might give you a z direction, but that's not going to happen. I don't know why that keeps going away. There we go. The conservation of momentum is especially useful in dealing with explosions or situations involving propulsion or the force of thrust. If we consider our system being a rocket, including the fuel on board, then initially the momentum is 0 if the rocket is at rest. After the fact, the rocket is thrust forward, but likewise the gas is exhausted downward. And the sum of the momentum, the rocket plus the gas, has to equal 0. Notice that the gas is in the negative direction, so we'll end up with a minus sign in here once we take care of our vectors. So let's do another example involving explosions. Squids rely on jet propulsion, a versatile technique to move around in water. A 1.5 kilogram squid at rest suddenly expels 0.1 kilograms of water backward to quickly get itself moving forward at 3 meters per second. If other forces, such as the drag force on the squid, are ignored, what is the speed with which the squid expels the water? So I'm going to draw a picture. This is my squid side view, and he contains ink. So he's got initial velocity, let's see, he's at rest, I think it said somewhere. So initially, my initial momentum is 0. And he's got some mass, I'm going to call it mass of squid. Yeah, mass of squid. And the mass of the squid, SQ for squid, is equal to 1.5 kilograms here. Yeah, here it says he's at rest initially. So my initial momentum is indeed 0. He suddenly expels 0.1 kilograms of water backward. So this is my initial situation. My final situation has the squid being propelled in the forward direction, right, with some velocity. He looks kind of like a ghost. It's good Halloween. So here's a V squid final right here to the right, but then he has some water that he's ejected out of him that has some velocity in the negative direction, V water, and I think it's supposed to be ink. So let's call it ink, right? He squirts ink out of him, and he expels a mass of the ink of 0.1 kilograms. So the mass of the ink is 0.1 kilograms. Okay, and his speed here, it says 3.0 meters per second. So the velocity of the squid final is 3 meters per second. And we got the mass of the ink or water, whatever he's squirting out of him. What is the speed with which the squid expels the water? So I want to know the velocity of the water that I'm calling the ink. Okay, so I've got this set up. Here's my final momentum, right? The only forces in here are internal. The force of the squid on the ink is a Newton's third law pair with the force of the ink on the squid. So, actually, let's do it this way so I can still see what's up here. I'm going to use my law of conservation of momentum. P final is equal to P initial, but my initial momentum was 0, so that's easy. My initial momentum is the momentum of the squid, which is positive, minus the momentum of the ink, which is negative because it's going to the left, and that equals 0. The momentum of the squid is the mass of the squid, except now in the final situation, and I should put, final here, final, the mass of the squid has decreased by 0.1 kilograms, hasn't it? So it's a different mass than it was in the original situation because that mass of the ink has now left him. So mass of the squid final times the squid's final speed minus the mass of the ink times the final speed of the ink is equal to 0. So I can look for this one, the final velocity of the ink. So M ink, V ink final is equal to M squid final, V squid final. Divide both sides by the mass of the ink. Boom, boom. I'm going to write it over here. V ink final is equal to the mass of the squid final times the velocity of the squid final, divided by the mass of the ink. So the final mass of the squid is the mass of the squid originally minus the mass of the ink times the velocity of the squid final over the mass of the ink. And I'm running out of space, but that's okay. I can squeeze in the numbers here. The mass of the squid was 1.5 kilograms. Oh, there we go. 1.5 kilograms minus the ink was 0.1 kilogram. I'll double check. Yep, 0.1 kilogram times the velocity of the squid final was 3 meters per second divided by the mass of the ink, 0.1 kilograms. And if you plug that into your calculator, you should get 42 meters per second. Now that sounds like a very large velocity compared to other things that we've had, cars driving, so always around 20 or 30 meters per second. So if I convert this into miles per hour, that's about 94 miles per hour. So yeah, it's pretty fast, but it makes sense that the ink with such a small mass goes very quickly relative to the squid who has a much larger mass and therefore moves much slower. So there are a couple examples for how to solve conservation of momentum problems. See you next week, or see you on Thursday, depending on which class you're in.